How's it going, guys? So we're going to do some MATLAB sim mechanics, SimMultibody. Keep calling it sim mechanics. It was formerly known as mechanics, but it's actually SimMultibody. Now what we've done so far is we've absolutely gone through these mass spring damper again and again and again. Now it's time to have a bit of variation. Now what I'm going to try and do in each one of these little tutorials, like I've said from the start, is I'm going to try and just use one tool and show you the benefit of this tool, and then you can choose where to use it or not. Some of these tools I probably won't show in class, and it just gives that little bit of extra curveball in all this, if you will. So without further ado, let's kick off. You'll notice I'm actually in SolidWorks. Now I've been on GrabCAD, and one thing that I've recently bought, I don't know if anybody's ever done this, but I bought these little gears, these little plastic nylon gears. Great for making little tool gearboxes. Phenomenally good for making little gearboxes. And it got me to thinking, if we're doing a gearbox, there is a gear function in SimMultibody. Let's have a crack at actually getting these gears to interface. When you're first putting these ones together, it's a huge pain in the backside. You're never 100% clear what the hell you're meant to be doing. So without further ado, let's open up. Again, this was downloaded from GrabCAD, and it is plastic gears, little plastic gears. Whoever the guy is that did this, he did a cracking job, to be fair, because all he's done is he's actually used design tables, so you can have the full range of gears in one gear, if you will. So those of you who are comfortable with design tables, you will well know exactly what I'm talking about. Now if you've downloaded this, I'm going to just nip over to here, which is my configurations manager. Click onto it, and you'll notice here he's gone through every single option that you can get these nylon gears. Cracking job. I'm really impressed, to be fair. So I'm going to double click onto my 40 teeth configuration. Boom, happy days. Okay. There's a couple of things what I'm going to do first. So just to give it a little bit of an old spin round. So what I actually need is, I want MATLAB to do all the moments of inertia for me. I'd like it to be as accurate as possible, so at least I can play around and be pretty sure about what's going on with it. So what I'm going to do is go to Save As, and I'm going to go to the desktop, and I'm just going to create, we'll call it Gears Sim. Alright, and then I'm going to, oops, double click into there. Now don't save it as a part. I'm actually going to export it as a step, AP214. The step files, they claim that they're a lot more accurate. The resolution on the clouds are far better, and I won't lie, actually I've actually found this myself. They are very good, very good. So I'm gonna go plastic gear, change that, and I'll call this teeth 40. Whoops, save that. And to keep this as simplified as possible, I'm going to go from 40 to 10, so my ratio is practically at nothing. So 10 teeth, do the same again, Save As, and I'm going to go Desktop, Gear Sim, drop this, step AP214, and there's my step 40. Oh, I nearly overwrit it. I'd be very upset. And I'm going to change that now to 10. So now, just to let you know, the reason it's always doing that is because the configurations table are here. So technically this part has one name and it's recognized as one part, but the configurations table allow you to have variations. It's great. I love configurations. Clearly, well, I think that's coming across. So I'm going to say save, and now we should have 2 step files. So let's check it out. So I'm going to double click into my gear sim. Whoops, wrong screen. 2 step files. Happy days. If you've not done already, start up MATLAB. And once you've started MATLAB, sorry, I'm just getting everything in the right place. So everything starts up. Now, this is things you need to keep in mind, and always remember this about the paths. What we're going to do is we're now going to tie all these paths together, and we're going to make it so that when it runs, what it will do is it will always look for the step file, so it can always import the step file. If you don't add the path to the step file, when you next run your simulation, it will crash. So keep that in mind. Always add your path. So go back to Gear Sim. I'm going to right click, scroll down, add to path. We can just go folders. I always go folders and subfolders. It's just because I've had some bad experiences before where I forgot to add the subfolders and it crashed again and it left me going berserk. So I do this even though the subfolders element is a redundant action that I'm going to ask it to do. So I add it anyway. Right, so if I double click, you'll notice now, if I go back, you'll notice my new folder here actually is greyed out, but my gear sim is coloured in. It's defined. This is purely because the system says, right, I recognize it, I'm going to use it. So I'm going to double click in, and we've got our 2 step files. Right guys, let's actually kick off with this. So let's go new, Simulink model. I'm obviously on the automatic start page here. I'm going to go blank model, because that's how I roll. Whoops. And now what I'm going to do is go to library browser, and I said Simulink library browser. I mean, really it is Simulink library, but I'm going to go on the library browser. Right. Now, we're going to stay with a lot of the tools that we've done before. So first things first, let's get all the way down to SimScape. Then from there, get all the way down to multibody, extend that. So, if you remember from the mass spring damper, we needed to establish the world environment. These type of conditions, we always need a world. We always need that starting point. We need something to tell us where gravity will be active and how it's going to be working. So what I'm going to do, first things first, SimScape, utilities. I'm going to use MATLAB's solver methods, because I trust MATLAB. Then I'm going to go to frames and transforms. Need a world. We need to establish where it is. We need to establish what that relation is going to be. Let's spin that round. And finally, if you remember, we need a mechanism configuration. Or I can spacebar. So I'm going to spin that round. Now at the minute, because we're going to be driving through torque in this case, or we could drive through momentum, we could say what our angular momentum is. We could, I mean, as you know, this system will allow us to choose however we want to drive it. It needs to be realistic, so don't start to think that you can measure torque in meters or measure fluid in millimeters. It's just a stupid, it's a silly ratio, but you know what I mean, right? So if you remember from the last one, I was always talking about it needs to know exactly what that first level of relation will be. Now all we're going to do is we're going to get the 10 gears to interface with the 40 gears and then just drive. That's what we'll do, and this simple process will allow us to look at how it interfaces, and if it's right then we can, you know, crack on. However, if we need to change things, it's quite easy, you know, it's dead straightforward. So first things first, let's start bringing in that relation. So for frames, apologies, not frames, joints, I'm going to try and get everything to activate itself in the Z plane. Well, you know what it's like, it just means I don't have to mess around with trying to figure out where everything's going to sit. It's me being extremely lazy, but one thing I've learned about this system ever since I was doing it for PhD, try to simplify everything that you're doing. You're simplifying this process as much as possible, because yes, this is 2 gears, but what if it's a gearbox? What if you're then looking at nubs between each point? What if you're looking at a new type of bearing? You want to try and prioritize that bearing, but make sure that everything else has a simplified approach to it, because it's purely Occam's razor of where the simplest answer tends to be the right one. So we've got us rotational joint. Next thing. Now all this is saying is what we're going to add to it will allow it to rotate. It's actually not saying anything sophisticated and sexy past there. What I'm going to do is go back to bodies and elements. I'm going to bring in a solid. What I am starting to do now though is I'm moving a bit quicker, just because we've gone slow through a few things. We're going to move a bit more with some excitement to it. Now I'm going to rotate this round. I want to hang this off the top. You'll see what I mean. So I'm going to press Control and R. This brings it round. I always like to rename these. So I'll call this 10. No, I won't call this 10 teeth gear. It just allows me to have a clear definition of what the hell I'm looking at, or else this is going to get very messy, very confusing, and not help anyone. So let's bring that in. Right, now I know we've not done much of this, so first things first, let's take a look at the joint. So I'm going to open up the joint. Look at this beauty. Right, now I say this, obviously some guys look and go, that's lovely, well done. So let's open up the state targets. We're not going to change these, I just want you to see these. Specific position target. We can specify where we'd ideally want to be, where we'd ideally want to move up towards, or anything like that. You should remember though that when these specific targets are added to a position, it will just go 10 straight away. And it's in these type of conditions, it's actually hinders what you want to do. Okay, so specific velocities, yeah, fair enough, running up to a certain speed. It's not too accurate as to how you'd want it to be. You do want a bit more of efficiency to it, but it's nice as a test. You can run these up and just see if it's going to do what you want it to. It can be hit and miss with resilience to how it plays with other blocks. For this, I'm going to actually turn it off. I don't want that, so I'm going to bring that back. Equilibrium position. The ideal position. It will always desirably hit these positions at each time. Now you'll notice everything's recorded as a rotational unit, purely because we are in a rotational element. This is simply saying everything that passes through this element will rotate around, hang on a second, the Z-axis. I was highlighting that just so you're aware. This purely rotates around that Z-axis, so always keep in mind that when you first add it, everything defaults itself to Z, and you are responsible to make sure these things move and change exactly as you want them to. So, spring stiffness. This is referring to if you're looking at particular motors that have bearings, or you have coils that cause a second order type behavior. The reason that they refer to it like this is it's a system dynamic. Often the damping coefficient is used as more of a equivalent of damping around a joint. So basically something is holding up that joint. So it could be interference of some sort, it could be particles, it could be rust, it could be failure of the bearing. So they refer to it more as a damping purely for this reason. It's an interesting one, is that, because you can start to look at what happens when the joint begins to fail. Because the trouble is in engineering, if you make a declaration of this is rusted, or this is I don't know, the bearings failed, what everybody does is just looks and says, oh, it's just the bearing, we'll just change the bearing. But if you say this is the condition of the joint when it's damped, when it's failing in these states, this is how it looks, what people say is, oh right, okay, then if it's rust, if it's one of these elements, this is the type of behavior that we're looking at. So it's a very flexy type term. You can have kinetic friction, you can have Archer's law acting purely within this. So I mean, that's what we are going to do, but this is like a, I don't know, like a flexy way of doing it. So what I'm going to do is just keep that empty. Now actuation, we're going to come back to this, but actuation, motion controlled and torque. Exactly, torque, you need that torque to be calculated. In some states you kind of go, right, I don't want the torque for this, I'm only interested in this component, this component, this component, these torque areas that I'm most interested in. It drops the level of computation needed and gets you your result that much quicker. Sensing, well, I'm not actually going to read out what these are, because, well, I mean, they're obvious. This one, however, composite force and torque sensing. This is a tricky one. Right, so let's just pull this to the side. Look at the base, then look at the follower. So if the torque's going this way, which in our case it will be, but it may be going this way, you just don't know which how you've configured this. So you look here, I can go look at the base to follower, so base to follower, or you can go follower to base. And what this is implying is the tooth will be onto here, and then there will be a torque acting around here, because it's, in essence, it's pulling it round. So these are some of the things to keep in mind. So yeah, the lower ends here, these are quite interesting. So the resolution, this is the main target of what you're looking at. What's the main focus that you want within it? And the constraint force, the torque, the total force and torque, you can take from sensing and from the total that's coming out from your target. It just depends what you're more interested in. If you're interested in the stress around the actual joint, the bearing, so to speak, that's what you can do. So let's move on. Okay, into the tooth itself. At the minute it's on the brick. What I'm going to do, drop the shape, go to file. You'll notice here it's down a step. I want to stay in step. I'm going to go to my find 10 teeth. I'm going to go 10 teeth because that's my 10 teeth step. F5, and there's our tooth. What I want to do though, I actually want to stay with the different colors because it can get very confusing when these things are interfacing. So I'm going to go graphic, sample, and in here I want to change this. I'll probably change it to a white. It actually stays then with what the original colors were, if you remember, in SolidWorks. Now, for the love of the money, I cannot remember what the value was for nylon. So I'm going to go nylon density. 1.15 grams per centimeter cube. So I'm going to go inertia, density 1.15 grams centimeter cubed, update, all of the moments of inertia, products of inertia, centre of mass and mass all pre-calculated. F5, and we are ready for business. Oh, I love this job. Right, so next step, we need to have the gear interface. This can be a huge pain, but let's try and make this as painless as possible. So let's go back to the library, and what we're going to do is we need that force and torques. I think it's under force and torques. Let me just check. No, gears and coupling. Let's get these mixed up. So I'm going to drop my gears and go into gears. You'll see that you've got all these different ones, bevels, stuff, but they all function on the same principle of what we're going to discuss right now. So I'm going to go to common gear constraint, drag and drop this little bad boy straight in there, and I'm going to lock this into position. Now we need to go back to SolidWorks in a couple of in a couple of minutes, just because you need to be clear about why we're actually configuring these things and how and in essence why we're doing this. So what I'm going to do is open up my gear constraint, and let's bring that up to the top, so we can go center distance to ratio with a gear ratio to the center distances. I personally like the pitch circular radii. So we've got the base, so in this case 10 tooth is the base, and we're going to put on the follower, but so let's just find out what they are. So I'm going to go back to SolidWorks. So there is his gear, so I'm going to get onto here and I'm going to do a sketch. I normally put a sketch on these, it's only just because I'm just arguably I'm just a little bit lazy. What I do this for is, you'll notice I located that onto there. I'm going to put on a circle, come from the center, and I'm just going to bring it into that edge. This is not the most accurate way of doing it, so when we take a dimension from this, what we need to find out is what this is, and we will need to round. So I'm going to go smart dimension, take it from this edge, and it's 9.93. So I wonder what the radius of that would be. So that allows me now to go back. Let's just go back. Let's go big. Where the hell have I put that? Right. So you remember 9.93. So we're going to round it. Ready? 5. Up here for thinking, down there for dancing. Right. So we've got that on as base. We're coming in. We've got that. It now knows that the internal ratio for this gear that's coming from the 10 tooth, that the radius from it is 5 millimeters. You'll notice I've just changed these to millimeters as well. It's just because if I don't, I will forget, and then we'll end up with a really weird simulation. So I'm going to go back again. Now we are using, I've forgotten which. Oh, come on, you swat. There we go. Right, so now we are using 40 teeth. And what we're going to do is go smart. I know what a lot of you are thinking. You're thinking, yeah, but it's a 40 tooth. It's obvious, like, but, what if you come across a different time? What if you need to be able to measure it a different way? I'm just trying to show you how these things interface, so if you are screaming at me, don't. Right, so I'm going to do the same thing again. Just draw a line across. Gives me that centralized point. Happy days. I'm going to draw a line to my midpoint, which will be my pitch. I'm going to take my dimension, and like a magic, it's 39.98, so which instantly tells us that that radius must be 20. Has to be 20. So let's go back onto that radius. We're going to go 20. So we now know, based on the base, The base gear is the 10 teeth. The follower tooth is the 20 tooth, but it's the radii, not the diameter. So keep that in mind. It's just, a lot of people do look and go, I'm sure that was, trust me, it's the right one. Right, I've right clicked, so I'm copy and pasting. Now what I'm going to do here is change this to 40. I'm going to remove that one from the front. So what I did again is I right clicked and then just dragged out, and it's a super quick way of copy and paste. So if I go right click, right click, right click, right click, right click, right click, right, you get the picture. If you don't want to do that, select it, Control V, Control Z. It's just a quicker way of doing it that way. Right. So let's get into here. Issue that we've got is we're still registered under the 10 tooth. What I need to do is change its location 10, and we're going to go 40. Really, I could have changed the actual title. That would have done it. Bring it round. Now again, you'll notice that we're in white. I want to change that. I'm going to change that to the red. It just, I mean, oh, not pink. Red. Ah, that'll do. Well, we'll find out. Let's go F5. Yeah, that'll do. Right. So I'm going to connect that to the front. Now, let's save this. We're going to call this, I'm going to call this gear teeth. Or gears. Sodding gear teeth, tell you. Right. So that's gears. And see if this is going to work. It's going to hit run. Yes! Look how well that's worked. I'm just messing. I meant it to do that. Right, that's exactly what I was looking for. I mean, I'm not trying to be the world's worst comedian. That's exactly what I was looking for. There's a few issues in this that we need to fix yet. We need to, in essence, this doesn't know how it's going to move. Don't forget, this gear here knows it can move round. This interface between the common gears knows that they're interfacing. So this 5 to 20 has been put into position, which is bang on. Happy days. But still, it doesn't know where everything's going. So we're going to have to go back. Just delete that. We're going to have to go back and we're going to have to put things back. Right, so now we've got this joint here. So I'm going to right click, drag. This is where it gets a little bit confusing. So I've got a joint that's interfacing. This is my base, this is my follower. I'll think of it as back and front. I want to replicate this behavior here, interfacing with this gear and mirroring it across. So what I'm going to do is select the gear, select the joint, spin that puppy round, and I'm going to connect it to that point. This is purely because I need the gear, I need the common gear constraint to stay in control of everything that's going on, and because they all meet in the central point here, it means any changes that are made will always be mirrored across from both sides. It will be able to pass between the two, which is ideal for what we need. Right, so sadly it still doesn't work. What we need to do now is we need to consider, well, in fact, let me just run this. I want to show you why it won't work, rather than just, let's say, just ignore this for the minute because it's going to complain. Right, this is one of the biggest problems that students, myself, everybody I can think of have ever had it before. We need, you think about this rotational joint here, this is fixed at the world. It knows that this point is not going to move. We want to recreate this over here, but technically, if we go back to the drawing, But technically, if you look here, it goes in and then it says it's revolving, but it doesn't know where the hell it's going. So let's try something. Bring this in. So by theory, could we not just connect it up and make a loop? Let's try running it now. Okay, so what the hell's happened now? So I spin this round. It's now sitting central. It's brought in an error because it's saying, well, I'm 25 and this isn't 20. It's just confused. It's not clear about how it's moving. So instantly it kind of looks and goes, I have no idea what you're trying to do. You're being a dick. So I'm going to delete that, run it again. Yeah. So this now means I need to find a way to allow my joint to be at the distance I need it to be and then translate back in. I know, right? Very, very annoying. Very annoying. So what I'm going to do is go back to the actual frames, come back into the library. This library again is your saving grace. If you're not comfortable with this, I'd always recommend running through this again and again and again, getting really confident with it, because it is your ultimate saving grace. It really is. So what I'm going to do is go to my frames and transforms. What this allows me to do is move things around. I can move along components to say this joint is sitting here and this joint is sitting here. It's what we need to do. So I'm going to drag and drop. Now, this, what I'm saying is this joint's going to sit here. What I need to tell the system is that this joint is sitting over here. So what I'm actually going to do is say at the base, this point, let the gear, the common constraint gear, control it. So I then bring this in. So then once it comes in, what it says is, oh, it's alright, this one's controlling it. And what we're going to get the rigid transform to do is return it back to home, which is where this started. So then I'm going to drag this and connect it. Now, granted, I've not shown you what the rigid transform is yet, but let's double click in. Rigid transform is simple. So think of it as an axis, an ultimate axis. You can say where things move. You can say how something translates. I can rotate the axes. I can tell it, you know what, don't use Z, use X, use Y. I mean, we're going to use these again and again and again, but I can go all over with it. Or I can translate the relation from one to another position. Now with translation, all it's referring to is a distance across. So if I go down to translation, it then goes, okay, so you got translation, how do you want to do it? I'm going to go standard axis. So I can go Cartesian. For those of you who don't know, Cartesian, X, Y, Z component in millimeters, yards, feet, miles. I'm going to drop that down again. I'm going to go standard axis. This basically says, okay, if you're going to move something simpler, shall we just move along one of the components? And ironically, because we're doing gears, why the hell not? It should do the job perfectly. So I'm going to go millimeters for an offset. And I'm actually going to move it. I'm going to try for a start of moving it minus Y. So in any other stuff, you've always known that you've got minus or positive based on the component axes. The same conditions, but with this it likes you to define plus or minus. If you've got Cartesian, you actually put the minus in. So it's just things you got to get used to doing. So the offset, I'm going to freeze for a second. Do you know what the offset is? So what we're attempting to do is return it home. What we're trying to do is return it back to its positional state of where it originally came from. The offset is simple. The offset is actually seen here. Think about it. We've told this system to move 20 mil and 5 mil between two components. So obviously, as it's moved along 20 and 5, we're going to move back 25. So let's see if that works. Oh, what's happened? Ooh. Oh, now that's a good start. That's a very good start. I mean, what I'm going to do is just run that once more. Now, the reason I say it's a good start is nothing's crashed. And it really is like that. You kind of look at first and you go, oh, nothing died, everything's running, it's working. And in essence, yeah, that's what we can rule out with it at the moment. But we need to move forwards. So we've got these components. If I first thing I do not like, which I'm sure a lot of you have already seen, zoom in. Not a fan at all. That is not what we wanted. That is very frustrating, in fact. Very frustrating. Right, so let's try and fix that. Now I should point out this is basically a visualization of what it is that we're actually doing. But when you're running a simulation, there's nothing wrong with trying to make sure that it's tidy, it's well presented. This is not well presented. In fact, it's a bit poor. So I'm going to right click, copy that across like that, spin it up. Don't forget, this is a translation tool. This will allow me to move stuff. So let's get into translation first, and I'm going to get rid of it. So I don't want any translation. I don't want it to move along the axis. Rotation, however, again, I'm going to go standard axis, and we're going to go, let's have a look at that. Given where that sits, I think I'll actually move in the minus Z component. You could go in the positive Z because it does look quite central. And I'll go 20 degrees. If I measured this, it will allow me to be even more accurate. But I just want to see what it's going to do. Yeah. Oh! Let me just come. Let me just come back out. Don't forget, the base is saying from the original. Then the follower is actually saying the new position. So I'm going to spin that round. I'm going to lock that in. Right, now try it. There we go. I mean, really, it's still a little bit connected. Yeah, it is still a little bit connected, but let's move forward. So I'm going to come back in, and I might just let's go 21. See if that helps it. Yeah, I think that actually hindered it. I'm going to go back to 20. It's going to stay with 20. I could go back and measure it, but what I'm interested in here is that. So I'm just going to hit run again. Excellent. Now I know it sounds incredibly patronising when I'm running, but the only reason I'm very pleased with that is that it's not crashing. It's working. It's doing its job. So let's start introducing something. Now, for a nice test, I often like to run, just as a test, to make sure this is running. So I'm going to come into here, and I'm going to say this is the point where my motor is going to be interfacing. I'm going to double click in, and remember when we're looking at state targets, I'm going to go velocity. Oh, 5's already in there. So in fact, I'll go 10 degrees per second, and then I'm going to run it. Nice. Okay. So I'm going to go. What I'll perhaps do is, if this is my gear, I'm going to double click in. This is my motor. I'm going to go sensing, and I'm going to do an automatic computed. This can often crash, so I just need to check if this is going to work first. Yeah. It's to do with the degrees of freedom that's present within it. It's a bit frustrating, really. It is really frustrating. We can do it if we provide an input, which I mean, to be fair, we probably would have to provide an input. Let's bring that out. Now, because we have weight acting on it, what we'll do is we'll go to sensing. I'm going to go to actuator torque, apply, and bring that out. Now you see, now we've got this little bad boy here. This bad boy is in essence now looking for that power stream converter. That's great, because what we're going to do is go back to the library, swing straight back into the library, and we're going to go to SimScape Utilities, and we have power stream to SimScape converter. What we do is bring that straight up, and we're going to locate that round, bring that into position. And then what we can do is, well, we can actually set the units in there if you remember. So I can go Newton meter or whatever, but what I'll do is keep that a solid state for the moment. I can change that, I will do. So I go back to Simulink, and I'm going to bring in commonly used Berlux. Go to scope. Just going to go with single port, tag that in, and then just zoom that. Then let's run it again. Nice. So let's bring in the scope. Yeah, look at that. It's done a cracking job. There's not really going to be much there. It's just purely because it's trying to pick up on elements, and we could try. Let's try on a total torque. The only trouble is with total torque, it can be a little bit of a pain, really. So it's purely because there's no real drive behind it that this is emerging. I mean, when you look now, what this is doing is it's recording from every single component. Interestingly, this is to the power. This is to the power of 7. Wow. So in short, not much. It's just because there's not much there. So let's bring that back, bring that torque into there, come back onto there, and then let's get to sensing. And I'm just going to remove that total torque. I don't like all these, I don't like messy wires. I am a bit of a silly sod when it comes to messy wires, things like that. Whoops, sorry. That's what I'm about to add. So finally, what I'm going to do is I'm going to actuate this torque. I want to make it move. I want to make it something that's useful. So I'm going to go actuation, and I'm going to go input. So we're going to tell this thing that we're moving to a present state for a present movement. I'm going to go back to the Simulink library, come across, and let's go back down. Let's go to utilities, and we're going to go from Simulink to power stream conversion, which is in essence the replica to the other one that we were using. So I'm going to bring that in, and this one's a bit more trickier, because what we need to do is we need to tell it that it's going to be behaving like a motor. We need to tell it it's going to do what a motor would do. Basically, any motor will have a second order behavior. There are coils within it that gives it that overshoot and that damping, the spring behavior. So I mean, we don't have to put that in, and we're not going to, but we're just trying to provide a filtered input so we can let MATLAB do that for us based on what's driving into it to give us that behavior of a motor. So I'll go filter input, derives calculated, derivative calculated. We're going to go by first order filter. Now a first order filter would imply that there is no mass applying to it. It is simply two components of a K and a C value. So what I'm going to do, drop that down and go second order. Now we have that mass spring damper effect, but it's the effect. It is not a spring itself. So I'm going to go back to units, and in the units what we've got is not what I'm looking for. Damn it. Yeah, I'm just messing. So if I click on here, if I can't find it, I can always say, you've got it wrong, I want degrees. Apply. Right. So now what we're going to do is we're going to bring in a signal builder. Signal builder. Oh, excuse me. So scroll back to the top. Going to go sources. This is in Simulink. Bring in, drag in and drop a signal builder. This will allow me to design, in fact it's what's jumped on the screen a second ago. This allows me to decide how the motor behaves, what level of degrees are put into it. It's not an engine, don't forget, we're looking at how that motor interfaces, so I'm going to double click in. Now you'll notice here I've got all this square function. It's not a square function that I'm after in this case. What I'm after in this case is I just want the motor to move to a present set, and what I want it to do is move sensibly. I don't want it to move like it's going 300 sodding miles an hour. So you'll look across here, and I'm going to change that to add constraint constant signal. This signal here, clicked on it, right click, delete that signal. Yerp. So now we've got a signal basically backwards and forwards. I'm going to left click once on the edge marker here. We've got time finishes at T, but we have Y. Now what I was messing around with before, this is crazy, what I was messing around with before is I ended up putting it, God, I think I'd have to double click it back in. I think it was 600 degrees. I was just playing around, just looking at different values. So bring that back out, get rid of this, and then let's connect that. So let's run it. Right guys, yes, I just realised something. Wonder why it crashed. I've just made the most stupid of mistakes. I'm actually trying to calculate the torque, and I've just said I'm going to actuate it. What a wally. Right, what I actually want it to do is tell me what that torque's going to be. So I'm going to automatically... That was totally my mistake. So I've double clicked back into the Revolute joint, and in the torque here I've now changed it to automatically compute. What I'm actually going to do is I'm going to drive the position of the motor. So motion is now provided by me. If I add that in, what you'll see now is it changes from torque to Q, which now refers to its rotational behavior. So if we run this again, it's the type of behavior it should be getting. So let's have a look how the torque gets on. Okay, so let's analyze this further. I'm going to bring this down. I'm just going to look at this. So looking at this, I mean, as you can see, it's very minor. This sharpness here, we could tidy that up, but we're looking at what? 0.1 to the -7, so 6 will be micron. So it will be 0.00 micrometers of microns of Newton per. Wow, that's short. Okay. Right, yeah. So let's just swing back to this point. This is our most important point. This is the momentum. You got to think about it. It's going to apply that momentum to it. You're going to get an overshoot on it. This overshoot, if you do not have enough power in a motor to achieve for this overshoot, and you really need to tidy up them time steps, but if you do not have enough power there, what you're actually going to end up with is where it will fail to do it, and the motor will draw more current, and you'll end up at a point where it will stall. Some motors will continue to try to deliver it. They will heat up, could burn out. Some motors will just cripple under the force that's been applied. If you've got too much weight acting on something, the gearbox that is supporting that will cripple and it will not survive. You've got so many variations that can occur with it. So let's just take an estimate of this. We don't know what units that are actually, so let's just get back into here. Let's just set some units. Let's go. Oh, Newton meter. Let's try that. So this is in Newton meter. Okay. So this is 10 to the minus 5 Newton meters. So this is 0.0005 Newton meters of torque at the highest points over here. But it's actually just beneath 4. So in essence, if we went to the shop and let's have a look. Let's see. DC motor torque. So we're going to go, let's just go 1 Newton meter. Might as well. I mean, look at that. So what if we went 0.5? 0.5 Newton meter there. Wow, that's, yeah, we don't need that much. Okay, let's just drop that down to 0.0 Newton meter. Oh, you look at that. So you look at that. We've got 7.8 meter per Newton meter. 0.0. So we drop another one. £10. Look at that one. This one looks like a winner. Winner, winner, chicken dinner. Let's have a look at that. So, maximum torque, grams per centimeter. Output of grams per centimeter. So that's the maximum. RPM. Yeah. So we've actually found ourselves a motor. This would suit. I'm scoping this much higher than it needs to be. A tenner, and that will drive. Well, to be honest, it's like 100 times better. But what I'm able to do, what I'm really trying to show is that I'm able to look at it, select it, go to it, and then check it, make sure it's right. And let's say we've got some idiot who thinks, I know, I'm gonna stick some glue on it, or just something really daft. Let's go to inertia. What I'm going to do is I'm going to add a damping to it of 0.5. 0.5 Newton meter of damping is massive. So let's run it again. Get back in here. Oh, damn. Look at this. So let's get back on. Okay, that damping is actually, if I get back to the actual simulation, it should jam. Oh, that went really well. It actually didn't. The worst thing is we've taken a 20mm gear that's taking 30 Newton meter of torque to move. 30 Newton meter. There's some engines that don't need that level to move. Basically, we've knackered it. This was just an idea to show you that. Right, so if you've not done already, guys, make sure you save it. Don't forget to export. We've already gone through how to change this onto the desktop, so it's on MATLAB. I hope you found this a benefit. Some of these things, this one in particular, I will not be covering in class, just purely because I want to put a bit of competitive edge there, have a bit of fun with it. So please do keep in mind that this is not going to be in the notes, so this is just for those who are just keen to learn more and more about MATLAB and some of the extra cool things it can do. If I've not said it sooner, if there's any questions, please drop by my office. You're always welcome to come and have a chat about cool stuff like this, and I hope you found it a benefit, and I'll speak to you soon.